Heidi-ho, Renaissanceteers, and welcome to the presentation of solutions to Renaissance puzzle number 45, the square deal. If you have not already viewed the puzzle itself, I recommend that you do that first. Otherwise, this presentation will not make a lot of sense, and you'll have missed out on all the fun of trying to solve a really ingenious and challenging problem with lots of opportunities to be creative. So, I'll give you a moment to stop this video. Well, I went down south for to see my gal singing Polly Wolly Doodle all the day. Okay, if you're still here, it means that you want to see the solutions, or you're just curious about what this silly looking guy with a goofy hat is going to be doing next. So, here we go. Solutions to bracing the square. This puzzle was devised by Raphael Robinson at the University of California, Berkeley. Professor Robinson is renowned for determining the minimum number of pieces required to solve the Banach-Tarski paradox. Here's a bonus opportunity. Write an explanation of the Banach-Tarski paradox that is understandable to the average high school freshman and win a Renaissance point. This puzzle was published in Scientific American magazine, November 1963, in the Mathematical Games column, edited by Martin Gardner. In a later issue, Gardner published two solutions by Professor Robinson. Both solutions used 31 bracing rods, plus the 4 rods of the square. Gardner invited readers to send in their own solutions, and in the February 1964 issue, he reported surprisingly that 44 readers had found a better solution than the renowned mathematician, using only 25 rods. Even more impressive, 7 readers had come up with a 23-rod solution, bettering Robinson's solution by 8 fewer rods. Is there a better solution yet? Perhaps you will stun the math world by finding it. 4 different solutions will be presented here, starting with the most obvious and working up to the cleverest, using the least number of bracing rods. So let's get started by looking at some building blocks to a solution. We know that triangles are rigid structures. So let's take 2 triangles and join them together so that their common edge becomes 1 rod, and they are joined at 2 corners. As you can see, we have formed a diamond, the hardest substance known to man. So we know that's got to be rigid. That was a joke. But seriously, it is rigid. And we can join more triangles, as many as we like, to construct a rigid truss as long as we like. In this case, we have a truss of length 4. Does this remind you of anything? How about this? Choo-choo! Train bridges have to be very strong. They make extensive use of triangular bracing. Okay, now that we know how to construct rigid trusses, let's construct 3 trusses of length 3, 4, and 5. And let's arrange these 3 trusses to form a triangle. Now the 3 trusses form a triangle of sides A, B, and C, where A equals 3, B equals 4, and C equals 5. Pythagoras taught us that if A squared plus B squared equals C squared, then you have a right triangle. And indeed, 3 squared plus 4 squared equals 5 squared, which is 25. So we know that this is a right angle. Now all we need do is add 2 more rods to complete the square. And voila, we have a braced perfect square. If you count the rods, you will find that there are 4 rods for the square, plus 43 bracing rods, 47 total rods. So this is a valid solution, but not a minimal solution. We can do better. By the way, The integers 3, 4, and 5 are called a Pythagorean triple. There are an infinite number of Pythagorean triples, that is, sets of positive integers, that satisfy the equation a squared plus b squared equals c squared. Therefore, there are an infinite number of solutions to this bracing the square puzzle. To find more Pythagorean triples, pick any two positive integers, m and n, where m is greater than n, and then find the values for 2 times m times n, for m squared minus n squared, and m squared plus n squared. For example, let m equal 3 and n equal 1. This gives us the value for a of 8, that's 3 squared minus 1 squared. The value for b of 6, that's 2 times 3 times 1. And a value of c of 10, that's 3 squared plus 1 squared. So, carry on with the math. We see that 8 squared is 64, 6 squared is 36, and 10 squared equals 100. Add the first two numbers together, a and b. 64 plus 36 equals 100. So we have another Pythagorean triple. But 3, 4, and 5 are the smallest integer values that satisfy the equation a squared plus b squared equals c squared. And we are looking for even smaller solutions using less rods. So let's find another approach. Let's start with our first solution using the 3, 4, 5 triangle and trim it down. To a 2, 3, C triangle. And what is C? Pythagoras tells us that c squared equals 2 squared plus 3 squared equals 4 plus 9 equals 13. Therefore, c is the square root of 13. So how can we construct a truss of length square root of 13? To figure that out, let's get familiar with our triangles. All the connecting rods are equal length, so the three sides of the triangle are equal. This is called an equilateral triangle. 6 equilateral triangles fit together to make a hexagon. And since there are 360 degrees around a circle, all angles must be 60 degrees. Now let's figure out the height of a triangle. Draw a vertical line from the apex to the base. This divides the triangle into two right triangles of sides A, B, and C. Pythagoras says a squared plus b squared equals c squared. Therefore, b squared is equal to c squared minus a squared. And if you do the math, you find out that our height b is equal to the square root of 3 divided by 2. Now let's build a truss with 6 triangles joined together, like this. And calculate the length c of the red diagonal line. Now, the x-axis shows a length for the x component of c of b is equal to 3 1/2. And the vertical direction, we have a is equal to the square root of 3 divided by 2. So going through the math, we find that c squared is equal to 13, and therefore c is equal to the square root of 13. That's just the length we were looking for. So let's put this length truss in the figure below. Ah, shucks. The red truss overlaps the square, and that's not allowed. But we can fix this. Let's first remove the interfering triangles. Then we add some new triangles on top. And voila! Now we have a brace with no overlap.
There are 4 rods for the square, plus 31 bracing rods, 35 rods total. 12 fewer than our 3, 4, 5 triangle. This is the solution that was given by Professor Raphael Robinson, the puzzle's author. But there are still better solutions. The Matt Fisher solution. As we determined earlier, the height of our triangle is the square root of 3 divided by 2. Matt stacked a second inverted triangle on top for a total height of square root of 3. Then he added 2 more triangles as braces to form a rigid curved truss. Next, he created a mirror image of the first truss and connected these 2 trusses to a base truss of length 2. Then he tilted the 2 vertical trusses toward each other until they connected in the center, forming a rigid structure. We already know that the length of a tilted truss is the square root of 3. Draw a line from the junction of the 2 vertical trusses to form a right triangle of height A and base 1. Pythagoras says a squared is equal to h squared minus 1 squared. Do the math and you find that a is equal to the square root of 2. The square root of 2 is the same length as the diagonal of a square with sides of length 1. So all we need to do is put our square in this place. And voila, we have a braced perfect square. In this figure there are 4 blue rods and 25 black rods. This beats Professor Robinson's solution by 6 fewer rods. But wait, there's more! Let's look next at what Jeff Merrow did. Jeff created 2 mirror image trusses as shown below. Then he tilted them towards each other until they connected at the top, and added a single rod brace at the bottom. Hey, this looks like a right angle. Add 2 more rods, and you have what appears to be a braced square. Wow! There are 4 blue rods and only 17 black rods bracing it. Did Jeff beat Professor Robinson and the entire readership of Scientific American? No, I'm sad to say he didn't. This may look like a right angle, but it's not. You can prove that it is not a right angle using only the information already shown in this presentation. But you may need a calculator to determine exactly what the angle is. That will be the next Renaissance puzzle. The puzzle description was clear. You must create a perfect square, like this one. So we cannot accept the red quadrangle below just because it is nearly square. Otherwise, someone will come along and say, well, if you accepted that, then this one's got to be good too, right? And someone else will say, oh, well, if you're going to take that, then how about this? And someone else will say, well, maybe this one here is good too, huh? And someone else will say, oh, well, if you're going to accept those, go for this one. And then someone else will say, well, how about this? You got to take that too, huh? And then someone else will say, well, here, this is almost a square, and so on, until where do you drop the line? That was another joke. Alas, though I would love to see a new world record solution come from our own little Société Renaissance, a near miss is still a miss, and close only counts in horseshoes and hand grenades. So we can't call it a solution, but I'm sure you would agree that Jeff Merrow's clever design is worthy of at least 1 Renaissance point and an honorable mention. So let's review the solutions we already have seen so far. There's the 3, 4, 5 triangle with 43 bracing rods, Professor Robinson's solution with 31 bracing rods, and Matt Fisher's solution with 25 bracing rods.
So, Renaissanceteers, you've now seen 3 valid solutions to the puzzle of bracing the square, but you've not seen the best one yet. Do you remember that 7 readers of Scientific American found a 23-rod solution? Well, I'm proud to say that one of our very own Renaissanceteers, Jim Kirk, has also found a 23-rod solution. Would you like to see it?